What we will do today is look at the various quantities that you will encounter in chemistry, physics, mathematics, and so on, that are either infinitely small or infinitely large. You have seen previously, perhaps at school, first year certainly have seen it already, that such quantities are difficult to manipulate directly. You cannot divide 0 by 0 or multiply infinity by 0. You don't know whether the answer will be 0 or infinite. So we will today introduce the tools that allow you to manipulate infinitely large and infinitely small quantities. In particular, where we will use them later is in the definition of derivatives, in the definition of a definite integral, and also the infinite time limit happens to correspond to thermodynamic equilibrium. And so it will come up as soon as your kinetics and thermodynamics people catch up and start teaching you how the rates and yields of chemical reactions are described. Okay, so what we will now do is give you the tools to manipulate those quantities and the rules by which the various infinities operate in mathematics. But we need to start with a little bit of introduction, so the first item on the agenda today is called sequences. And a sequence in mathematics is exactly what the name suggests. It's just a set of numbers accompanied by a rule on how to generate those numbers. So a sequence is a set plus a rule. And there are two types of rules that we will encounter that generate our sequences. One is the so-called explicit definition. So let's say our sequence here is A1, A2, A3, and so on. It can go to some finite number or can go all the way to infinity. And explicit definition is when you are given an explicit formula in terms of the index of each element. So let's say this goes to an, and we are then given an as an explicit function of n. For example, n equals n squared. In that case, we can trivially build the sequence. We know that a1 is equal to 1, a2 is equal to 4, a3 is equal to 9, and so on. An is n squared. More frequently, however, in physics and chemistry context, you are given a recursive definition. Second type. This is when the next element of the sequence is defined as a function of the previous elements of the same sequence. For example, we can say n is n plus 1, an minus 1. It's a kind of formula. Let's look in detail at how this might work. Let's say we are given a 0 here, and we are told that it's equal to 1. Can we find out what the other terms of this sequence would be? Well, we can start thinking. So a1 will be n is equal to 1, so n plus 1 is equal to 2. This is a0, we know that it's 1. So this is 2 plus 1 is 2. a2 will be n equals 2, therefore this is 3. a1 we know is 2, 3 times 2, 6. a3, n is 3, this is 4. 4 times a2 times 6 is 24. And so on. The reason why recursive definitions are preferred in chemistry is that very often in what you will be looking at, these would correspond to some time domain process. You know that concentrations of the chemicals in the reaction mixture at the next moment in time are functions of the concentrations at the previous moment in time. And so, in a way, the rule that gives you the concentrations at the next moment in time can be formulated recursively, and the corresponding equations the chemist will give to you in due course. What is important here, however, and the reason we are dealing with this is because these sequences can go out to infinity, and the next thing we introduce here is something called the limit of a sequence. The limit There is a rigorous mathematical definition, but of course we only have one lecture. This is mathematics for chemistry. So I will not give you the rigorous definition, I will give you the next best thing in terms of the end-waving definition of it. The limit of a sequence is the number, if it exists, that is an important qualifier, that this an approaches closer and closer as n becomes bigger and bigger. So, number, very importantly, if it exists. We will see examples when it does not. An approaches arbitrarily closer and closer as n goes to infinity. The notation for that is as follows. Say n goes to infinity a n. And let's take a look at a few examples. Let's say our sequence is defined explicitly and an is 1 over n. The limit n going to infinity of 1 over n. Let's think about what this might be equal to. When n is equal to 1, this is 1. When n is 2, this is 1/2, so it became smaller. When n is 3, this is 1/3, smaller still. When n is 1,000, this is 1,000th, tiny number. When n is a gazillion, this is 1 gazillionth. So this goes down as n goes to infinity, and the larger n becomes, the smaller is the structure. So when n becomes arbitrarily large, this becomes arbitrarily small, and so the limit of this sequence is 0 as n goes to infinity. If we look at a different function, so let's say the limit going to infinity of 2 to the n. Well, if n is large, then of course 2 to the n is even larger, and so this will go to infinity. However, if we look at a limit of something that is, for example, oscillatory, so limit n going to infinity of something called cosine of n. We know that cosine continues dribbling and bobbling, no matter how large the argument is. It just keeps on oscillating. And it will not approach any particular number, and so the number does not exist. So in this case, the limit does not exist. What this allows us to do is to, well, let me just give you another example from chemistry. The energy of the nth orbital in the nth quantum number in the hydrogen atom. You may have seen it at school, minus mu c squared alpha squared over 2n squared. So where mu is the reduced mass in the electron nuclear system, c is the speed of light, and alpha is the so-called fine structure constant, and n is the primary quantum number, 1, 2, 3, and so on, the thing that enumerates the periods of the periodic table. What you can clearly see, in fact, that as n goes to infinity, this would go to 0. And so the larger and larger atom becomes, the weaker the electrons are bound to it. And as you know from your chemical knowledge, that larger atoms are easier to ionize, all other things being equal than smaller atoms. And this is the consequence of this limit going to 0 as n becomes larger and larger. But okay, so let us look at where this is useful and how it is. And so item 2 on our agenda today is the manipulation of infinitely large and infinitely small quantities. Infinitely large and small quantities. These limits were kind of obvious, all of them. If you sit and stare at it long enough, you can say, well, I know what this limit is. Let us take a look at a limit that is not obvious. Something like the following. Limit of n go to infinity of 2n plus 5 over n plus 1. The numerator of this expression clearly goes to infinity. As n becomes larger and larger, this just also becomes larger and larger, just twice the rate. The same happens to denominator. Denominator also goes to infinity. And so what we have here is in fact one infinity divided by the other. Both the numerator and denominator blow up. But the fraction might not. So what is the limit of an expression where both the numerator and the denominator are simultaneously infinite? Let's have a good think about it. Limit n go to infinity. As n becomes larger and larger, let's put it into a couple of billions, relative to that number, 5 well, remains the same and eventually becomes insignificant. As this number grows to an arbitrarily large size, this becomes an arbitrarily large fraction. So for a large enough n, it doesn't actually matter whether we call it 5 or 3 or not. The same applies to the denominator. If n becomes sufficiently large, we can, as chemists say, neglect. There is a more rigorous procedure in mathematics, but we don't have the time for it. We can neglect these numbers relative to a very large number n. So this has to be equal to the limit of 2n over n, in which, of course, we can now cancel n. And so that is the limit n goes to infinity of just 2, which doesn't even depend on n, and that is actually 2. So the limit of a ratio of 2 infinitely large quantities happens to be finite. And this is probably the most basic example of a non-trivial limit, where you have to sit and think what that would be. In chemistry, this would be the concentration of something and the concentration of something else, and this would be time. And you know that at chemical equilibrium you have fixed ratios between concentrations of different substances, so you can see immediately where that would be used. Let us now look at another example. We can ask ourselves, okay, these were infinitely large. Let's now look at infinitely small. We will define two sequences explicitly. A n is equal 1 over 3n plus 5, and the Bn is equal to 1 over 3n minus 5, 3n minus 5. It is clear that both of these go to 0 as n becomes larger and larger, because n is in the denominator grows and grows, and therefore the fraction drops and drops. However, what we would like to know, which one of these sequences goes to 0 faster than the other. So which one goes to 0 faster? In order to determine that, let us consider the limit of their ratio. Look at the limit. A n divided by n as n goes to infinity. If A goes to 0 faster, it will overpower B, and this limit will be 0. If B goes to 0 faster, then the denominator will blow up faster than A has the power to decay, and so this will become infinite. So let us take a good look. Alright, so that's a limit n over to infinity of A is that 1 over 3 x 5. And then 1 over b is just this fraction inverted. So 3n minus 5. 3n minus 5 over 1. You can plainly see that we can cancel this and this. And so we are only left with 3n minus 5. Limit and go to infinity. 3n minus 5. And when n becomes infinitely large, this also becomes infinitely large, so this is in fact infinity. And so Bn goes to 0 faster. Or equivalently, when n is infinitely large, this 0 is bigger than that 0. So there are some infinities that are larger than others, and there are some zeros that are smaller than others in mathematics. And it depends on the rate at which they approach that 0 or that infinity as the index of the sequence becomes larger and larger. So that is one example. The next thing we need to do, notice so far, we have focused on the situation where the argument is discrete. n can be 1, 2, 3, 4, 5. It's an integer index. The next thing we need to do is to consider a situation where n is continuous. That is, we are not looking at a sequence, but we're looking at a function. Limits functions. And a limit of function is defined in a similar way as this, except in the case of n we could only make it go to infinity. In the case of a function we can put arguments to anything we like. So the limit of a function, limit x going to some fixed point x, not 1, 2, 3.5, whatever we like, f of x is the number f of x approaches as x approaches x naught. There is again a rigorous definition as to what does it really mean to approach and what does it mean arbitrarily closely and so on. But if you'd like to know that in those particulars, I will send you to the mathematics textbooks. It's all there. Or in fact, there are links to Wikipedia from your handout directly where you can see the super rigorous definition of a limit. But for our purposes, this suffices. Well, let's give a few trivial examples, then a few less trivial examples, and then let's put it to good use in some chemistry that we will have to do. Some limits are really simple because there's really nothing special. Nothing goes to 0, nothing goes to infinity, stuff to do. So, for example, limit x goes to 3, or whatever I got in the handout, x squared. Well, that's just plainly 9 because there's nothing special about x squared, nothing special about 3. As x bumps into 3, x squared becomes 9. Likewise, we can have x going to infinities, zeros, and minus infinities. So, for example, the limit x going to infinity, 1 over x. Well, we can see how x becomes larger and larger. As a result, the root becomes larger and larger. As a result, the fraction becomes smaller and smaller. Therefore, the limit has to be 0. Then we can look at various polynomials and so on. So, for example, the limit of x going to 0 of something basic like x to the 4th plus 6. Well, if x is 0, then this is just 6. Some limits this simple. There are, however, complications. If you look at, for example, the limit of x going to infinity cosine x, then for the same reason as that did not exist, this as x becomes larger and larger, cosine x keeps oscillating and does not approach any particular particular value, so this does not exist. However, if we were to put x to some other value, for example, pi, such the limit of x going to pi, cosine x, we know that cosine pi, whatever it was, minus 1, and so that is our limit. So this is trivial, this is slightly less trivial. Let us look at something serious. So non-trivial limits. Some of these people occasionally memorize, others there are recipes for, so I will give you the tools to calculate those limits, but let me give you an example. A limit x going to 0 of sine x over x. If you plot sine around 0, it looks like this. So at 0, the sign is 0. So we have a 0 in the numerator, and we have a 0 in the denominator. Now this limit happens to be equal to 1, and I will show you the methods that allow us to actually determine that that's the case in just a few minutes. Another non-trivial one is limit x, and x goes to infinity. X becomes bigger and bigger, but the power of the root also becomes bigger and bigger. So x tries to grow, but the root is pushing it back. Non-trivially, this is equal to 1. And then another interesting limit that is actually similar to this one. If you put x 1, so a cosmetic difference, this becomes equal to e. So why and what is happening in there? So our next topic is to try and find out the rules of how the limits are calculated. In figure 1 of your handout, I have given you a seriously anomalous case where a certain function begins oscillating infinitely rapidly at its origin, but the limit still exists. It is obviously 0 from the picture. Okay, so the rules of calculating limits. There are basic rules and there are more sophisticated ones. The two basic rules have one important condition attached to them. If two limits lim f of x and lim g of x, when x goes any way you like, so just this is true for arbitrary limits, are both finite, so not infinitely large and not infinitely small, so not 0 and not infinity. The following is true. Then the same applies to the product and the ratio. Lim of x, and exactly the same for the ratio. very important to keep emphasizing that these three rules only work when the limits individually are finite. So for example, it would not apply to the rules that we have here because both the numerator and the denominator are infinitely small as x goes to 0. So this is for like trivial algebraic simplifications of limit expressions when you know that individual limits exist and are equal to finite numbers. So the less trivial ones, the ones that we will actually spend some time discussing now. The first one is called identification of leading powers. So that's item 3a. Identification of leading powers. Let's take a look at something rather complicated. If we have limit root x to the 7th plus 1 minus x squared over x plus cosine x, and x goes to infinity, it's not clear where even to begin here, because what we have in the numerator is when x becomes infinitely large, well, that goes to infinity. The root does. However, x squared also does. And so we have infinity minus infinity in the numerator, which we don't know what to do about. Then we have in the denominator infinity plus something where the limit doesn't even exist, as we've already established. And so this is probably, so it's infinity plus something that doesn't exist, dividing infinity minus infinity. Not exactly a pretty object, right? And yet this exists and it's just fine. So let us think about how we would approach this. First of all, some functions grow faster than others. If you plot various powers, so let's take something simple like x squared and x cubed. X, and that will be some power of x. Well, the x goes like this, then the x squared goes like that, and then x cubed goes like this. So this is one. And as x becomes larger, it's clear that x cubed outruns x squared, becomes large faster. And x squared outruns x, and if we look at something like the logarithm, you know that the logarithm of 1 is 0, and so it will be some slowly going function like that. If we take the root, it will be slow. So some functions grow faster than others. Let us think about what we have here. In the numerator, as x becomes larger and larger, we can ignore this little 1 because it becomes insignificant. And then this is just power 7/2. So that's the limit x going to infinity of x to the 7/2 minus x squared over x plus cosine x. Well, power 7/2 is bigger than power 2. And so, as x becomes large, this infinity is going to be bigger than that infinity. And eventually would outgrow it so much that we can ignore the x squared. So that goes faster. It's called the leading power. Then in the denominator, our x is growing to an arbitrarily large number, but the bigger little cosine will always stay between plus and minus 1, so eventually we'll be able to ignore relative to x. And so this must be equal to the limit of x to the 7/2 divided by x going to infinity, which is the limit x to infinity of x 1/2, which is clearly infinity. What we have done here can be written roughly also in the following way. We have an object here where the numerator is of the order of x 7/2, and the denominator is of the order of x. And this O notation tells us that whatever this thing is, it asymptotically, right, in the limit of very large x, behaves like x to the 7/2. And whatever is in the denominator up to the various terms that may become insignificant behaves as something of the order of x. And of course, when x is large, then that becomes infinity. So this is the method of identification of leading powers, or perhaps more generally, the method of finding which functions grow faster than others or drop faster than others as x approaches 0 in the case of decaying things. So another example of where this works is limit x going to infinity. In the numerator, we have a logarithm, 2x plus 1. In the denominator, we have a root. And something like this will take a bit of experience. You have to kind of compile a ranking table in your head as to which functions grow faster than others. In the case of logarithm and the root, you can make a plot again, x. So you know the root of 1 is 1, so it does this. That is our root. And if you plot the log, then it does this. It goes through 0 at 1, and then really slowly grows. If you go far enough, you realize that this gap between the root and the log increases. And so both of these functions grow slowly, but the log is slower. And so it's eventually overpowered by root x, and this limit is 0. As you can see, this is a combination of a bit of mathematical thinking and a bit of experience. And so it is absolutely imperative that you go through the problems that use these limits and that you continue practicing, because up to now, perhaps for first year chemists present, the school education has been about memorizing stuff and reproducing it in exactly the way the teacher expects you to. University education is about understanding things. And we do not enforce any particular formalities. If you draw a square and right underneath it is a circle in the exam paper, I will consider it a circle. Right? We are not formulaic. We are not even teachers. We are scientists. We do homework here. And so long as it kind of makes common sense, we are fine with that. But you can see there's an element of creativity. And that element of creativity can only be obtained through practice. Because then you've got the knowledge that tells you that log grows slower than root x, in fact slower than any power, even any negative power eventually. Alright, so that was 3a. 3b is perhaps simpler, but it's surprising how often people neglect this and have difficulty as a result. Just simplification. So let's have a simple example. Limit of 1 over x minus x plus 1 over x cubed plus x when x goes to 0. Well, that will be infinity. Cube is a stronger power than x, so, and a stronger power than x here, so the cube will go to 0 faster than x. You can clearly see it here, so the cube approaches 0 faster, and so in the case of infinity we had to keep the cube, because the cube goes faster. But in the case of 0, we have to keep the x because x drops slower. So in this case, we would have, when x goes to 0, it will be 1 in the numerator and x in the denominator. So we have 1 over x minus 1 over x. But infinity minus infinity, again, unclear what is going on here. What we need to do is to simply just try and simplify that. Let's put it under the common denominator. Now what we will have there is just multiply things around. So limit x to 0 of. Well, if we want to bring it under the common denominator, we need to multiply and divide that by whatever's left. So it will be 1 over x, 1 over x squared plus 1, and then x squared plus 1 minus there, x plus 1 x. So I multiplied and divided the first fraction by this, with the result that the denominators are now equal, so we can subtract the numerators. Limit x to 0 of x squared plus 1 minus x minus 1 over x cubed plus x. 1 cancels, 1 unit of x cancels, so that one disappears, that one disappears, and then a single x can be cancelled as well, so we will have x plus x minus 1, and then we will have x squared plus 1, and x goes to 0, and if we put x to 0 here, this is actually standard, right? So the limit of the numerator is finite, the limit of the denominator is finite, and so we can use that rule to simplify further. So that is the limit x to 0 of x minus 1 over the limit x to 0 of x squared plus 1. This limit is clearly minus 1, that limit is clearly 1, so that is minus 1. So the strange subtraction of bizarre infinities ended up being equal to minus 1. So in this case, this infinity is bigger than that infinity by exactly 1. You can see how philosophers might be rather puzzled by this, but of course we are superior to philosophers. Okay. The next thing is applications. So we're chemists, and so let us put some chemistry into the picture in the remaining minutes. The first thing we'll look at is the case of chemical kinetics. This is something that the first years have not yet had, so we will simply approach it mathematically. Say, somebody told us what the time dependence of concentrations is in a chemical reaction, and then we want to know what is going to happen when we have waited for a very long time. So reaction is quite simple. It's A K plus K minus into B, so forward and backward reaction between two things. For example, cis trans-isomerization across some double bond. Clever chemists that second years present already are, and the first years will become by about Christmas, told us that the dependence of concentrations on time is as follows. The initial concentration of B times K minus 1 minus E minus K plus K minus T, and then plus K0 K minus plus K plus E minus sorry about there's a bulky arithmetic here, but you cannot take a word out of a song. This is what these concentrations really look like. Once you've done the proper chemistry on them, K plus K minus, and then the concentration of B as a function of time is something very similar. A naught k plus 1 minus e minus the same bracket t plus b naught k plus k minus e to the minus the same bracket t divided by the same denominator k plus k minus. What does it mean to wait a very long time? This means t goes to infinity. So we've been sitting around for an infinite time. Let's see what is going to happen. As you know from common sense, chemical reaction rates are positive. That is, you have E minus K plus K minus T. This bracket is positive. This time is positive. And so this must be equal to 1 over E, some bracket, and then T. That's a positive number, that's a positive number. If t goes to infinity, this becomes e to the infinity, that's an even bigger thing, and so this goes to 0 as time goes to infinity. Well, let us apply that. So when we put t to infinity, all 4 exponentials are going to cancel. So a at infinity, and this is understood that we have taken the limit in the proper way. So that becomes b naught k minus, that disappears, plus a naught k minus, over plus k minus. And b of infinity is likewise a naught k plus. This exponential goes, and then b naught k plus over k plus k minus. A very considerable simplification. And let us now look at what the ratio is equal to. So a at infinity over b infinity will be b naught plus a naught plus numerator divided by k plus k minus over a naught plus b naught k plus, so that's actually k minus in here, k plus over plus k minus. This cancels, k minus over k plus. Equivalently, b at infinity over a at infinity is k plus over k minus. The second years will recognize the definition of the equilibrium constant of a chemical reaction. So because that's the asymptotic ratio of the concentrations of the two substances. So limit of time going to infinity in fact provides connection between chemical kinetics and chemical thermodynamics. So you will see that rather a lot. I have another example in your handout that relates to the rates of chemical reactions that are more complicated. It's sort of considered in detail there, but let's look at it briefly. So the rate of nitrogen production by dt in a reaction of nitrogen monoxide with hydrogen is K1, K2. The concentration of hydrogen, the concentration of nitrogen monoxide squared, divided by the reverse rate of some first reaction in the multi-stage process times into H2. Let's think about the various limits here, particularly as related to the concentration of hydrogen. If the hydrogen concentration is really, really small, we will be able to ignore this. And then the reaction rate becomes linear and that concentration proportional to the concentration of hydrogen. If the concentration of hydrogen, on the contrary, is really, really large, then we can ignore that. in which case it will cancel, and so reaction rate would actually stop depending on the concentration of hydrogen. And so in this case, these are not genuine limits, because there's no way to make the concentration infinite, but these will be approximations as the concentration becomes larger and larger. In this case, the reaction rate will apparently stop depending. And conversely, as it becomes smaller and smaller, the reaction rate would start being proportional to it. And these are generally signatures of complicated chemical reactions when such behavior happens. And you will see that a lot in your various practicals, for example, when you are exploding the mixture of hydrogen and oxygen. The final thing to notice is, the two great big theories that supersede Newtonian mechanics, the theory of relativity and quantum mechanics. When you take the limit of the speed of light going to infinity, so you have relativity, and the limit of speed of light going to infinity is Newton's laws. Relativity is so complicated precisely because the speed of light is finite. If you make it infinite, you recover the classical mechanics. And quantum mechanics is so complicated because there's something called h bar, the element of the phase space, right? The smallest possible unit of quantization that you have. If you put that to 0, you get back Newton's equations of motion. So the two theories that prevent things from going arbitrarily fast or becoming arbitrarily small, if you actually allow things to go arbitrarily fast or become arbitrarily small, you go back to Newton's second law. But both transformations are limits. I will not go any deeper into this because all three objects here are horrendously complicated individually, but the relationship between them is limits of something going to infinity and something else going to 0. Okay, so the summary of the lecture is, I think, rather philosophical. Is that some zeros are smaller than others, and some infinities are bigger than others, sometimes by 1. And this is real, and we will be dealing with that every day. So you can now divide by 0. Congratulations. And we will be using all of this when we define derivatives and integrals.